Hey folks, today we're going to talk about significant figures. So what we're going to do is we're going to discuss what significant figures are, why we use them in science, how to use them, and then finally we'll talk about some mathematical operations with significant figures, both adding and subtracting and multiplying and dividing, which each of those pairs of operations require slightly different sets of rules. So we'll explore those towards the end. And to be frank, this video got a little bit long. You may be taking a look at the timestamp underneath your screen, longer than I would have liked. And so your familiarity with this topic of significant figures may vary from yourself to another student. And so feel free to just, scan around to what you need to, all right? There should be links or there should be chapters down below the video to each of these different sections of the video. And then for every explanation for a discrete scale, like how to use significant figures, adding, subtracting, and multiplying and dividing, I go and work through some of the solutions for the problem set problems. And so all of those are in the chapters below, or they are linked to each specific section in the worksheet, in the digital worksheet itself. So feel free to jump around to wherever you need to. And if you think and you need a little bit more explanation, take a look at that section. If you want to skip a section, you can do that. All right. So go right ahead. Use your discretion. So in order to explore what significant figures are and why we use them, I like to pose the question of when did the dinosaurs die, which is a question that you probably know the answer to. And if you don't worry about it, but you may have come across it in other classes or just from your own knowledge about dinosaurs. The answer is, if you're curious, 66 million years ago. However, more importantly to our discussion here, I want you to think about what does that number mean? Meaning, I'm recording this right now and the year is 2026, right? So this year, we say the dinosaurs died 66 million years ago. What about if we fast forwarded 1 year to 2027? How many years ago would the dinosaurs have died then, right? What if we fast forward 10 years, the year 2036, 100 years, so 2126? When do we start saying that this 66 million years ago becomes a different number, right? We know intuitively that next year in 2027, we're not going to say a different number. We're not going to say, oh, now it's 67 million years ago the dinosaurs died, right? We crossed the threshold from 66 million to 67 million. But would we say that it's 66 million and 1 years ago? Obviously not, right? So in this number of 66 million years, we have an implicit and intuitive sense that there's a level of precision that isn't precise down to the 1 year mark, right? Right. So we know that 1 year from now, we're not going to change this number 66 million years ago. In 10 years from now, we're not going to change the number to 67 million years ago, right? So we know there is some level of precision here communicated by this number. What is that amount of precision? And that's ultimately what I want you to think about with this number of 66 million years ago. How much precision is involved in that measurement of 66 million years ago? And hopefully the idea of precision or the concept of precision is not one that's foreign to you. But in case it is, let's go over a few basics here in terms of what accuracy, precision, and just numbers in science are. The first thing to think about is that in science, we have these things called physical quantities, all right? So physical quantities are going to describe a property about an object, like a water bottle, a system, like our economic system, or a phenomenon, like a thunderstorm, an event that happens in the world. And all those things, object, systems, phenomenon, those can be measured and quantified. And when we do that, we would give them what we call a physical quantity. So we describe the properties of the systems with a physical quantity. And those physical quantities, we're going to describe and we're going to collect data on them using some instruments, right? Something that will measure that object, system, or phenomenon. So, for instance, if you go into the doctor's office, the doctor is going to collect some data, some physical quantities about your body, the object, the system that is your body. They'll collect things like your weight, right? Like your height. They'll collect your body temperature, your pulse, your heart rate, your blood pressure. So there's a bunch of things that they will quantify about the system that is your human body. And all those things we'll get numbers for, and they'll either be accurate or precise based on the measuring instruments they use to gather those numbers. And so for accuracy and precision, let's describe what those are. Accuracy is the degree to which a measurement aligns with the exact, the true, or the standard value for a quantity describing a system. So for instance, when you go into the doctor's office, if you know that your height is 5'6", and it has always been 5'6", but then the doctor takes out their ruler and they get a measurement for you that's 6'2", and you might want that measurement to be true, right? Or maybe you don't. But no matter what, you know that that measurement is not accurate. Their ruler was not precise, either in itself or in the way that they used it, because it didn't collect a measurement that aligns with the exact, the true, or the standard value for that quantity of your height that it was trying to measure. So a measuring device will be limited by its level of accuracy. Another way that it can be limited is in its level of precision. And precision is the degree of consistency and repeatability of a measurement. So for instance, in the doctor's office, if you step onto the scale and the scale gives you a reading of 160 pounds, then you should safely be able to say that your weight is 160 pounds. However, if you step off and then step back on again, and then it gives you a measurement of 148 pounds, then apparently that measuring device, that scale, is not terribly precise, because your weight obviously did not fluctuate by 12 pounds worth of difference by the time that you stepped off and then stepped back onto the scale, right? So its level of precision is off. It isn't being very precise and probably isn't being very accurate either. But precision is the degree of consistency and repeatability of a measurement. So if you step off a scale and step back on, it should give you the same number each time if it is precise. All right. So our level of accuracy and our level of precision for a measurement is dependent on the measuring device that we're using. All right, so to help us look at a real-world example of quantities and measurements, let's take a look at my friend over here. This is Maddox. He's one of the neighborhood cats. He's been hanging out with me today. He's actually underneath my seat. It's a hot one, so he's hanging out on the porch to get away from the sun. So Maddox has some amount of weight to him, and we'll explore what that weight is in a moment. All right, but if property for any physical system is going to have a quantity that exactly describes that property. However, the number that we're going to use to describe it has to be some rounded version of that exact number, right? Because however we describe a property for a system or an object or a phenomenon, we need to use some measuring devices only going to be precise to some amount. And so we're going to round that exact value to whatever amount our measuring device will allow. So my friend Maddox here is going to have some weight, right? And if we brought him to the vet, we'd be able to get a value for his weight. However, that value has some exact amount to it, right? So if we were able to measure his weight to an infinite level of precision, which we can't really do in the real world, we'd be able to get some specific number that accurately and exactly describes his weight. Let's say that number is 12.183792, it keeps going. We can keep adding digits right to the billions, to the trillions, to the quadrillionths of a pound, okay? But let's say, just for succinctness, that his weight is 12.183792 pounds, all right? So when we measure his weight, if we went to the vet, we would take his weight on a scale. That scale is only going to be accurate, only going to be precise to some level, right? So let's say that the scale was a very precise one, probably way more precise than the vet is going to use. But let's say it was precise to the hundredths of a pound. And in that case, then this number would be rounded to the hundredths of a pound because the scale is not able to tell us his thousandths of a pound or 10,000ths of a pound or a millionth of a pound, right? So it would round his number. So if it's accurate, then it would give us this number just rounded to the hundredths. So it should read 12.18 pounds. Now, the vet probably doesn't have a scale that's that accurate because it doesn't really have to be, right? Dealing with bigger animals, even smaller animals, the hundredths of a pound really isn't going to matter that much. So probably it's most vets that I visited anyway are usually accurate to the tenths of a pound. So in that case, then this number on the scale, if it's accurate, will be rounded to the tenths of a pound. And this number rounded to the tenths of a pound will be 12.2 pounds, right? So that's what the scale would tell us. Now, it wouldn't be able to tell us that his weight is 12.18 0.183792 pounds exactly, right? Because only precise to some level, and that precision to the tenths of a pound. So it would read this rounded to the tenths of a pound, and so it would say 12.2 pounds. And if the scale is even less precise, which some vets, dealing with bigger animals don't need to go to the tenths of a pound. So if it's even less precise, maybe it's only precise to the 1 pound digit, and so it would just say 12 pounds at that point, right? So you'll see that each of these scales gives us a different level of precision, a different level of information relative to this exact number. That if we had something that was more and more precise, we could get a better and better, more specific measurement for the weight of Maddox, this cat here. And so, why does this matter? And you may not think it matters all that much. However, when we start comparing objects, it does kind of matter what our level of precision is, right? Because sometimes they may look very similar in one property. Other times, if we have a larger level of precision, we might be able to differentiate between two objects. So, for instance, I have two markers, all right? One is a blue Sharpie marker, the other is a green Sharpie marker. And if I took and I measured these on scales that were accurate to the thousandths of a gram, we would see that there is some difference in the mass between these two markers. When I measured the blue marker, it came out with a measurement of 8.721 grams worth of mass. And then the mass of the green marker is 8.670 grams. Now, those two have specific masses. Again, if we measured it to the thousandths of a gram, we get those specific masses right there. However, in the classroom, in our physics classroom, our scales are actually only accurate to the tenths of a gram. So I took and I measured these two markers on our scales that are accurate to the tenths of a gram, and look at that. Each of them end up giving the same reading, 8.7 grams. Now, this makes sense, right? Because if we're only precise to the tenths of a gram, then if we rounded 8.721 grams to the nearest tenth of a gram, we'd round down to 8.7 grams, right? And if we rounded 8.670 grams to the nearest tenth of a gram, we would round up to 8.7 grams as well. So even though these two markers have different masses, our scale in the classroom isn't precise enough to tell the difference between the two of them. It gives the same reading for both of them, even though we know they have two different masses if we're being exact with their mass, right? However, our scales in the classroom are not precise enough to tell the difference, to differentiate between those two markers. And this is why precision in science is important, because we are limited in our ability to know the exact measurement for a property of a system or object or a phenomenon based on the measuring device we're using. And again, if we take a look at these two scales, this one scale I use in the classroom, this scale is not good enough to differentiate between these two markers. We know they have two different measurements if we were at two different masses, if we were able to be precise enough. However, if we have a limited level of precision, we may not be able to tell the difference between the two of them. And that's why precision is important. So let's talk about how we're going to communicate this precision in a number. So in science, it's important to communicate precision in our numbers. This is a little bit different than math, right? So in math, a number is just a number, meaning that if we think about the number 1, that it has no difference in meaning between 1, the digit 1, or 1.0, right? The decimal 1.0, or the number 1.00 or 1.000. We can have those zeros go on as long as we want. These are all the exact same number with the exact same meaning in math. However, in science, we're dealing with measurements. And so measurements can only be so precise. And notice that these zeros that follow the 1, we don't have to put them there, right? So we actually only put them there in science if we intend for them to be there. And what's happening here is that actually each of these representations, each of these expressions of the number 1 would tell us something slightly different would tell us something slightly different in science. Whereas in math, they don't tell us anything. They just tell us we're looking at 1. Right? So 1, if we just have the number 1 with no decimal after it, 1 kilogram, for instance, because since we're discussing a measurement, we would want to describe what units we're measuring in. 1 kilogram means that the object has a mass of 1 kilogram, and we know that mass to the ones place, meaning we know this isn't 0 kilograms, this isn't 2 kilograms, it is exactly 1 kilograms. However, if we went and we took that same object and put it on a scale that's a little bit more precise, perhaps one that's precise down to the tenths of a kilogram, then if it were really 1, it would give us a measurement of 1.0. And that 0.0 tells us something a little bit different, because now it's telling us that our 1.0, our measurement of 1, is precise to the tenths of a kilogram, meaning that we don't just know the difference between 1 kilogram and 2 kilograms or 1 kilogram and 0 kilograms. We actually know that this is not, we can differentiate between this 1.0 kilograms and 1.1 kilograms, or between 1.0 and 0.9 kilograms. So you see that we've narrowed down the range of potential measurements that would give us a 1.0 on a scale that's precise to the tenths of a gram versus versus the range of measurements that would give us 1 kilogram on a scale that's only accurate to the 1 kilogram spot. Obviously, we can go further with this, right? 1.00 on a scale that reads to the hundredths of a kilogram would mean that we know the difference between 1.00 kilograms and 1.01 kilograms, or 1.00 kilograms and 0.99 kilograms. So again, we've narrowed down that range even further. And so even though these 0.00, those extra zeros at the end of our number wouldn't really mean anything in math, in science, they're telling us that the instrument we use to collect this measurement gave us a value for that place value. And we know that place value is 0 because it could distinguish, that instrument could distinguish between that place value of 0 and a place value of 1 or 9 on the other end of that. Okay, so these extra zeros are telling us something. And in science, we call these extra zeros are significant figures or significant digits. We use those two terms interchangeably. So these extra digits here, they tell us a little bit something about the precision of the measurement that we collected here. So all of these measurements of 1, the 1 kilogram, the 1.0 kilogram, the 1.00 kilogram, they all have the same value. They're all 1, just like in math, right? However, they do have slightly different meanings. And the meanings, the extra zeros there, are communicating as something a little extra. They're communicating to us a level of precision, meaning how well do we know that, how close to 1 do we know this number is, right? And 1 kilogram, we don't actually know is all that close to 1. It could be as far as 1.5 kilograms. 1.5, anything under 1.5 would round down to 1 on a scale that only reads to the ones place. And anything above 0.5 kilograms would round up to 1 on a scale that only reads to the ones place. Whereas a scale that gave us a 1.0 kilogram reading, that we now know is has to be between 1.01 and 0.9 kilograms, right? 1.00 kilogram scale, if a scale gave us that reading, then we know it has to be between 1.01 and 0.99 kilograms. So again, these extra zeros are communicating, even though they all say 1, all three of these numbers say 1, they all have the same value, they're communicating something a little bit different to us, a slightly different meaning. And that meaning, again, is the amount of precision involved in that number. So now we kind of know what significant figures are. They're just a number of digits in a number that give us a level of precision for that number, and why we use them, because in science, the measurements are limited in our amount of precision, so we need a way to communicate those. Let's figure out how we're going to express that level of precision in a number that uses significant figures or significant digits. So there are some rules that go along with expressing a number with its correct number of significant figures. And let's take a look at this number down here. This is 0.002078 meters. This is some measurement that we came up with for the length of some object, okay? Let's keep track of the significant digits that are in this number, okay? And so there are 4 different rules we're going to keep in mind. Most of them have to do with zeros. Really, zeros are the only ones that are important here, because our first rule is that all non-zero numbers are always significant. So obviously, if we had a ruler or a measuring tape or something that gave us this number, then if it could measure this 2 here, then that measuring device is accurate to that place value, right? It wouldn't give us a non-zero number if it couldn't measure that place value. So right here, this 2 is in the thousandths of a meter, or the millimeter range. And so obviously this ruler or this measuring tape or whatever it was is able to measure that place value, that thousandths of a meter accurately, precisely. So any non-zero number is significant, meaning we have that number is precise, right? However, it's the zeros we have to look out for. So we have 3 different rules depending on where those zeros are in the number. The first one that's nice and easy is any zero that's in between 2 non-zero numbers is always significant, because if our ruler could give us a measurement for this place value and a measurement for this place value, then obviously it could have given us a measurement for this place value. This zero doesn't have no meaning. It means that the place value there, the digit for that place value, was a 0. It wasn't a 1, it wasn't a 9, it wasn't a 2, it wasn't a 7. We know it was exactly a 0 because obviously it's in between two place values that the measuring device could measure. So any zeros that are in between non-zero numbers are always significant. And then next one, so we'll give a little check over that 0 in between the 2 and the 7. All right. Then any zeros that are ahead of our non-zero numbers, that precede our non-zero numbers, those are never significant. So this 0, and this 0, all the ones that are before and after the decimal, before we get to that 2, that first non-zero number, those are never significant because our measuring device may or may not measure things that are that large. So we don't actually know anything about that, and we know that the property that we're measuring for our object or our system has no value there. All right, so there is no place value. So that's meaningless to us. Those zeros in front. Okay, so we're going to X those out. Those do not count as significant figures. And finally, there are zeros that follow our non-zero numbers, and those are sometimes significant. So these are the ones we gotta ask a question about. So we'll put a little question mark over that 0 after the 8 right now. And these zeros that are after non-zero numbers are significant if and only if there is a decimal in the number. Because if you think about it this way, if we put a decimal in a number, then any zeros at the end, we put there intentionally. If there is no decimal in the number, then we may or may not have put those zeros in there intentionally. So for instance, the number 2000, we would write, if we were accurate to the ones value or to the thousands value, 2000 has to have those zeros, those 3 zeros after the 2, to give it a value of 2000, right? Whether or not we have a decimal there. However, in this number right here, we could have written this as 0.002078. And in math, that would have the exact same value as this number that we wrote it as here, right? So this 0 right here does have a meaning to it. And it's because since we have a decimal here, we know that we communicated that 0 with a purpose. It's there for a reason because we didn't have to write it with that 0. So this one is significant. And for that reason, we'll put a checkbox. We'll say that this 0 is significant as well. And so if we counted up all these numbers that are significant, we've got 5 sig figs or 5 significant figures in this number. We have the 2, the 0 between the 2 and the 7, the 7, the 8, and the 0 that follows the 8. All right. So those are our 5 significant figures. And if we wanted to, we could think about what's the lowest place value in this measurement that we are accurate, that we're precise to. And that's that last 0 right there. And that last 0, it is the 10 millionths of a meter spot. So that's our least precise place value. And we have 5 significant figures in this number. So again, significant figures, we're going to track these 4 rules. So we'll practice again with another number just one moment, and then you will practice with these in our on our worksheet. So we've got those 4 rules. We'll go back through them in a moment, but they tell us how many the quantity of significant figures. In this number, there's 5 significant figures, and the lowest place value that we are significant to in the number as communicated. So let's practice with this number, 203 million. So we'll go back through our rules here. We're going to take a look at all non-zero numbers, right? So that's obviously the 2 and the 3. We'll put checks over them. They are always significant. Non-zero numbers are always significant. So we have 2 non-zero numbers. And then we want to take a look at zeros that are in between the non-zero numbers. Those are also always significant. So we've got the 2, we've got the 3. We have a 0 in between them. That's the 10 millionths place. The 10 millions place, right? And obviously, if our measuring device could read the 100 millions and the millions, then we could read the 10 millions place, right? So we know that 0 in between is significant as well. That gives us 3 significant figures at this point. In this case, and in many numbers that are large, we won't have any zeros preceding the first non-zero number. So there are no zeros in front of there. So we don't have to worry about them. What we do have to worry about are the non-zero numbers that are after all the zeros after the final non-zero number. And in this case, since there is no decimal, then none of these zeros are significant. So as this number is communicated, we have no reason to believe that any of these zeros are significant. So that means, again, we could count up our number of sig figs here. In this case, we only have 3 sig figs, and we can figure out what our lowest precise place value was in this number, and that was the 3 is the lowest place value that we have a significant figure for. So it looks like this number, as communicated, is accurate to the millions place value. Okay, so let's rewind real quick. Let's think about the dinos one more time. So they went extinct about 66 million years ago. So obviously the 66 million, we can communicate this with some level of precision that would give us an indication as to how precise that measurement of 66 million years ago is. And the paleontologists have determined that the timing of the extinction of the dinosaurs was 66 million years ago, with a level of precision that is accurate to the hundred thousands of years. And that means that the way that we communicate this number, if we were attending to significant figures and trying to communicate our level of precision of the measurement that we're communicating, is we would say that the dinosaurs died 66.0 million years ago, which means if we went forward into the future 100,000 years, then our number we know would change to 66.1 million years ago at that point, right? But until then, until we fast forward to some significant amount, next year is still going to be 66.0 million years ago, and 10 years from now it's still going to be 66.0 million years ago. We'd have to go really far in order to change this number because it is not that precise of a number, right? It's only precise to the hundreds of thousands of years. All right, and now that we can count up the number of significant figures in a number and figure out what is the least precise place value, let's put this into practice. If you click on this worksheet, if you click on the link in this slideshow, then you should be taking a look at our worksheet. We're going to take a look at part 1 and the problems therein. All right, so let's put all of this into practice. And for our first set of problems, we're going to count up the quantity of significant figures in a few different measurements, and we're going to try to find the lowest precise place value in those measurements. So for question number 1, we got 0.000002 kilograms. Obviously, 2 is the only non-zero number, so that one clearly has to be significant. All the other numbers in this measurement are 0, but they all precede that 2. So none of them, since they're all prior to our first non-zero number, none of them will be significant. And that means that we only have a single significant figure in our number. And if we counted what place value our significant figure is, we got our tenths, hundredths, thousands, 10,000s, 100,000s is our millionths place value. So our lowest precise place value is the millionths. For question 2, we have 800 newtons. Again, we want to find our our non-zero numbers. We got 8, and we know that's going to be significant. And then we've got our 2 zeros following the 8. And remember, zeros that follow our non-zero numbers, we always have to question whether or not they're significant, because sometimes they are, sometimes they're not. And when they are significant is when there's a decimal point that is explicit in our number. So in this case, we don't have an explicit decimal point, and that means that these guys are not going to be significant. So just like question number 1, we also have one significant figure, only a single significant figure in this measurement right here. And it looks like since it's 800, our hundreds place is the lowest precise place value within this measurement. All right, question 3, 1,030,000. Same thing, we're going to look for our non-zero numbers first, which we've got a 1, and we've got a 3, 1 in the million spot, 3 in the tens place. And so those, of course, are going to be significant. We know that any zeros in between non-zero numbers are also significant. And finally, we got that 1 0 off at the end. Remember, is that zeros after non-zero numbers are sometimes significant, sometimes not. Again, if there's a decimal point, then they are. If there's not a decimal point, then they're not. And so in this case, since we have no decimal point, that last 0 will not be significant. So it looks like we have 6 significant figures in this measurement right here, and our lowest place value where we have precision, where we have a significant digit, is the tens place value. Question 4, 14.9 watts. We have 3 different non-zero numbers and no zeros. So this one is nice and easy. We have 3 sig figs, and it looks like our lowest place value that has a significant digit is the tenths of a watt. Question number 5. We've got the number 180,900,000 Newton meters. We have 3 non-zero numbers, the 1, the 8, and the 9. We've got 1 0 that's in between the non-zero numbers. And then we have 5 zeros following our non-zero numbers. And again, all those we need to question if they're significant or not, because we're looking for if there's a decimal point. And in this specific number, there is a decimal at the end. And you might be wondering, this is not how we would usually write a number, right? A whole number and then put a decimal at the end. But you can include a decimal even when we wouldn't normally, if you're trying to communicate that all the zeros follow following the non-zero numbers are significant. So this is kind of unconventional, but what this does is this communicates anyone who knows what's going on with significant figures. This communicates to us that actually all those zeros, even though we wouldn't usually have this decimal point, that decimal point is telling us that all the zeros following the non-zero numbers are significant. So in this number, there actually are 9 significant figures, and we know that the very last significant digit, that 0 at the end there, is our lowest place value that we know to some level of precision, and so that's the ones place value. And finally, for number 6, we have another very small number, so 0.0000080, And as usual, our non-zero numbers are significant right off the bat. We have a 0 in between the non-zero numbers. We have all of these zeros prior to the non-zero numbers we know won't be significant. And so the only thing we have to question, as usual, is any zeros following the non-zero numbers. And that 0 will be significant in this case because we have a decimal point, right? So that 0 at the end there is going to be significant. And that means that we have 5 significant figures in this number, and the one that we know, the lowest place value that we know to any level of precision is that final 0, and that'll be, let's see, the tens, hundreds, thousands, 10,000s, 100,000s, millions, 10 millions, 100 millions, billions, 10 billions, the 100 billions. I guess I'll write that out. So that's the 100 billionths place value right there is the one that we know the lowest place value that we know to any level of significance or any level of precision. Okay, so at this point, we know what significant figures are. There are ways to communicate precision within a number that represents a measurement in science. We know why we use them, because the measurements in science are a little bit different than abstract mathematical numbers, and it's important for us to communicate how precise our measurements are. And we know how to determine the number of significant figures within a measurement that we're communicating. So now let's start talking about how we're going to do mathematical operations with these numbers that involve significant figures. So we're first going to start talking with adding and subtracting significant figures. So let's go back to our blue and our green marker. So again, we got our blue marker, we got our green marker. I took some more precise measurements of these markers, and we know from our more precise scales that our mass for the blue marker is 8.721 grams, and our mass for the green marker is 8.670 grams. And obviously, we can add those two numbers together. If we add them together, we would get 17.391 grams, all right? So we know, because we have a lot of information, a large level of precision for the mass of these two markers with our first mode of measurement, we know our combined mass of the two of them, how much they should weigh, how much mass they should have together, to a level of precision that has 5 significant figures, and that is accurate to the thousandths of a gram place value, right? However, remember that when we took these markers on our lab scales, we measured them, we only got 8.7 grams of the for their measurement, right? So let's say that when I was measuring the two markers in the beginning, I had a very accurate scale for the blue marker, and I got a measurement of 8.721 grams, but then that scale broke before I could measure the green marker. And then the green marker I had to measure with our less precise scale in the laboratory that only measures mass to the tenth of a gram. So at that point, now I've got a limited measurement for my green marker. All right, I have a more precise measurement for my blue marker, and I have a limited measurement for my green marker. So I've got 8.721 grams for my blue marker, again, accurate to the thousandths. But remember that our less accurate scale in the classroom only gave us a measurement of 8.7 grams, just down to the tenths of a gram. So now if I try to add these two numbers together, I get a different number than the combined mass when I added my two more precise measurements together, right? 8.721 grams plus 8.7 gives me 17.421 grams. Now I know that the real and exact and more precise combined mass of those two markers is 17.391. So this is not the same number, which is a problem because that means I know this is the wrong number, right? Those two don't match up. However, what can I do with these two measurements right here so that when I add them together, I don't get something that's wrong, but just a little bit less precise, right? Because the problem between these two numbers is that they're two different numbers, right? 17.391 is a different number than 17.421. Neither of them is the rounded version of the other. They both might round to some number to the same number if we rounded each of them. But one of them we don't have to round, right? This one we shouldn't round because we had these two accurate or precise measurements and we combined them and we got a precise number right here. However, this one over here, we got something funky going on with that one because it doesn't match up with the one that we know is more precise. Right? So let's think about what we're going to do here. We know that our two more precise measurements will get us a precise combination, a precise sum of those two measurements, right? However, with our more limited measurement over here on the right, combined with our more precise measurement for the blue marker, that gets a different number. So we're going to throw that number out. But let's think about what we can do with these two values, these two measurements, to combine them in a way that we don't get something that's necessarily wrong, but it's a rounded version of this, all right? So when we add and subtract measurements that differ in precision, what we're going to do is we are limited to the level of precision of the least precise one. And when we add two measurements together or subtract them, we're going to be concerned with the precision of the place value of these measurements. And I'll talk about why in just one moment, okay? So we're going to be limited to the place value of the less precise measurement. So if we take a look at these two measurements right here, the first one, the blue markers one, again, is the more precise one. This one is as precise to the thousandths of a gram. However, the green marker is less precise. It's only precise to the tenths of a gram. So what we're going to want to do is we're going to add these two numbers together, right? So we get 17.421, but then that number that we're going to get when we add the two numbers straight up together, we're going to take and we're going to round that off to the place value of the less precise of the two numbers we added together. And again, the less precise one is the green marker. It has a lowest place value that is higher than the lowest place value of our blue marker. So we're going to round to the tenths place, which is the lowest place value in our green marker's measurement, rather than the thousandths place, which is the lowest place value of the blue marker's measurement. This one's less precise, this one's more precise. We'll round to the less precise's lowest place value. So we'll round this off to the tenths of a gram. And when we take a look at that, now we have 17.4 grams is what we get when we add these two together and then round them according to this rule of round to the least precise numbers place value. And if we compare these two numbers together, now 17.391 and 17.4, those are the same number, right? One of them is rounded, but if we rounded 17.391 to the tenths place, we would get 17.4. So these are no longer two different numbers. They're just two numbers that are less precise. Still, it's the same value. One's just less precise than the other. So, so our sum with limited measurements is no longer different from our more accurate measurement. It's just less precise. And this is what we're going to do when we add and subtract two numbers when concerning their levels of precision. Okay, so let's do another example. So we're going to take these two numbers, 203.2 kilograms, and we're going to add to that 10.53 kilograms. Now, first of all, you may already notice something here, which is that both examples we've looked at so far, when we're adding numbers, the units that they are in are the same unit of measurement. And there's a reason for that. And that's that it doesn't make any sense to add two different units of measure together, right? So if you think about going into the doctor's office, if you get if your weight is 120 pounds and your body temperature is 97 degrees, think about adding 120 pounds and 97 degrees. You can add those two numbers together, right? 120 plus 97 would give us 217. But then what units would there be on there? Would it be pounds? Would it be degrees? Would it be pound degrees? It doesn't really make any sense. And if you think about combining like terms in mathematics, this is essentially what we're doing when we think about adding measurements in science. We need things to be like terms in order to add or subtract them in this way. All right. So our units always need to be the exact same. And when our units are the same, we're adding and subtracting two different measurements. Then you notice we can line them up based on their place value, right? So right here, I got this lined up based on our place value. So we got 203.2 kilograms with the tenths place right here. And then that's over the 10.53 kilograms with the tenths place again aligned. And so we can see quickly and easily what's going on in terms of their place values. So let's add these two numbers together, and then we can look at their lowest place values that still have some level of precision. So if we add these two numbers together, either in our head or with our hand or on the calculator, we get 203.2 plus 10.53 gets us 213.73 kilograms. All right. But obviously, we don't want to just add these two together mathematically. We then want to think about the precision that each of them brought to the table, right? So if we go back, we look at the two numbers we added together. The first one was accurate to the tenths of a gram, and the second one was accurate to the hundredths of a gram. So obviously, there is a difference there. And if we look at the first one, there's a bunch of different numbers, a bunch of different masses to the hundredths or the thousandths or the 10,000ths of a gram, that would have given us this number of 203.2 kilograms on a scale that is only accurate to the tenths of a gram, right? We could have had 203.21 kilograms. We could have had 203.17 kilograms. Both of those would have given us a reading of 203.2 kilograms on this scale that's only accurate to the tenths of a gram, right? And then, depending on how well we actually knew this number, right? We could have gotten 203.2457 kilograms. That still would have given us 203.2 kilograms, even though this is almost on the line. If it went up to 203.25, then that would push it over to actually read 203.3 kilograms, right? So we have a very large range of numbers, and there's a bunch of different decimals, a bunch of different digits we could have put into this hundredths place that still would have given us a readout on this scale that was only accurate to the tenths of a gram. That still would have given us a readout of 203.2 kilograms, right? So really what I'm trying to say here is that since this is a little bit less precise, really this hundredths place for our first reading, we have a question mark there. We don't know. It could have been a 1, it could have been a 7, it could have been a 4, could have been a bunch of different digits here. We don't know what really is in that digit because, again, our measuring device that got us that reading of 203.2 kilograms was not precise to the hundredths of a gram. So we lost information there that we had for our second reading, for our second measurement, that we don't have for our first one, right? And since this is a question mark, it doesn't really make any sense to add up this unknown place value right here with that 3 down there in the hundredths place value for the kilogram. So that's why this hundredths place value, it doesn't actually make any sense for us to keep that in the sum when we add these two together to get our final number. So we're not going to want to use 213.73 kilograms. Instead, again, we want to round. We want to round to the place value, the lowest place value of the least precise measurement, right? And again, since this is our first one, is our less precise one, and it was only precise to the tenths of a gram, we want to round to the tenths of a gram down here, and now we'll get 213.7 kilograms. And again, this elides for us, this glazes over for us that problem of what's going on with this hundredths place. So we don't know to a level of precision what's happening with that first number in the hundredths place, even though we do know with the second one. And since we can't add an unknown to a known number, since that would still be a question mark, that's why we just get rid of that hundredths place and we just round this to the place value of the least precise of the two numbers we were adding together. All right, and that is how we add or subtract numbers that while attending to their level of precision. Cool. Okay, so now let's go back to our problem set. We're going to take a look at part 2. We're going to practice adding and subtracting significant figures. So now we're going to add and subtract some numbers, and you'll notice I say add and subtract, though if you've taken a look at the problems, you might notice I only ask you to add some numbers. So we're going to add some numbers, and it, of course, works the exact same way as subtracting, okay? So we're going to add these up. What I like to do is I like to line everything up in terms of the place value. So we got 0.0012 joules, and we're going to add that to 0.360 joules. And you'll notice, first of all, that we're adding to quantities, to measurements that have the exact same units. And this is the only way that we can add two quantities or two measurements together, is they have to have the same two units. So if we take 10 centimeters and add that to 20 joules, that's an incoherent mathematical expression because those two things are not like terms. Just like in math, if we took 10x plus 3y, we can't add those two together and make one term together because they're not like terms. So we can only add measurements that are expressed in the same units. But if they are in the same units, then we can add them together. And so we got 0.0012 joules plus 0.360 joules. And obviously, if we just plug this into a calculator, we can just, or if we did this the slow way, so we got we're down to 10 thousandths, we have a 2, and then we have a 1, then we have a 6, 3. So if we add these together, we get 0.3612 joules. However, remember that we need to attend to significant figures if we're trying to be precise with the level of precision that's communicated in these measurements. And so we want to take the number, the measurement that we use that had the least precision. And in the case of addition and subtraction, because we're adding two things that are like terms, our definition for least precision here is the one that has the highest place value that is its lowest place value precision within that number. And so if we look at each of these numbers, the first one, 0.0012, the lowest place value is the 10 thousandths. But in the second number, 0.360, the lowest place value is the thousandths place value. And so since this one is higher, this number is less precise than the other one. This is giving us a less precise number of joules than the 0.0012 joules number. And so we will limit our precision of our answer to that place value, to the thousandths. So we will round off to that thousandths place value. And that, of course, gives us 0.3361. 2 will round down to 1 joules. And that is our answer. All right. And again, remember from our explanation of all of this that right here, since we don't know what this place value is for our second number, we essentially have a question mark in a 10 thousandths place. That means that could be a 1, could be a 2, or this could have been a 9 or an 8. We don't know what we're adding to this 2 right here. And since we don't know what we're adding to this 2, it's not really coherent or correct for us to use that 2 as if it's being added to a 0, which would produce this number, but that's not accurate because we don't know that second number to the same level of precision as the first one, right? So we will round to the least precise number that we're adding, and that would get us 0.361 joules. Question number 2, we're going to add 800 centimeters to 273 centimeters. So again, I'm going to set this up vertically. So we had 800, we're going to add that to 273 centimeters. If we add those two together, we can put them in the calculator, or we can just do this by hand. It would give us 1,073 centimeters. Though we want to go back and we want to check what's up with our level of precision in those two numbers. And so if we look at our first number, remember these two zeros that occur after the 8, those are not going to be significant figures because there's no decimal in this number. And so that means that the hundreds place value is the lowest place value to any level of precision within this number as that number 800 is communicated to us. And of course, if we look at our second number, the 3's place value, the 1's place value where the 3 is the lowest place value of precision within this number. But of course, that we're limited by between these two numbers that are being added together, the one with the least precision, and that is the one that has the hundreds place value. And so we have to round to the hundreds place value here. So if we take that 0.73 and round up, we will end up with 1,100 centimeters is our rounded answer. That is the level of precision we get when we add those two numbers together, the 800 centimeters and the 273 centimeters. And finally, let's add or subtract. Again, we're only adding these two numbers. So we got 20.34 milliliters, and we're going to add to that 10.7. Look at me. I'm trying to add more precision to this number. That's just 10.7, right, milliliters. So if we add those two together, we would get 31.04 milliliters. However, we want to round to suit the precision of the least precise of the numbers of the measurements that we added together. And so our first number is precise to the hundredths place value, but our second number is only precise to the tenths place value. So we will want to round to that tenths place value, meaning that our answer in the end should be rounded to 31.0 milliliters. We got to round off that hundredths place. All right, so now let's talk about multiplying and dividing significant figures because they follow a few different rules than adding and subtracting. Why might that be? Well, the reason is that when we think about a measuring device is going to have a range of values for which it can take accurate measurements for that physical quantity. For instance, if you think about the scale that you would use to get your weight when you go to the doctor's office, if we put a caterpillar on that scale, it's probably not going to be large enough to read any number. It's probably still going to say 0 pounds, even though the caterpillar obviously has some amount of weight to it, right? Likewise, if we threw an elephant onto that scale, it's probably going to break it. So there is a lower limit and an upper limit to any measuring device in terms of what it is able to measure. And depending on where our object or our quantity or our property that we're trying to measure with that measuring device falls, we're getting more or less information because it will fall either further or less far into that range of the measuring device's capabilities. So the further into that range the quantity is that we're measuring, the more information we're going to get from that measurement. And the less far into that range, the less information we're going to get. So back to our lab scales, if we take two different objects, we're going to get two different mass measurements. So a red Sharpie marker, I measured on our lab scales and gave a reading of 16.9 grams. And then my water bottle, I put on our lab scales, it gave a reading of 1,690.2 grams. Now, those are actually very similar numbers, right? 16.9 is 1/1000th or 1/100th of 1,690.2. However, you'll notice that the two of them end up giving us two different numbers, a different quantity of significant figures in the measurement that we produce from the scales when we're measuring the mass of these two objects. And it is for that reason that it is the number of significant figures that matter when we're multiplying and dividing numbers, when we're tending to significant figures. And another reason why is you can think about, so if we think about 1,690.2 grams, that's the same thing as 1.6902 kilograms, right? So we can shift around the place value depending on how we're expressing this number within the metric system. And so the place value actually doesn't matter all that much when we're thinking about multiplying and dividing. Whereas when we add and subtract, we always need things to be in the exact same units so that their place values do line up. And so if we take a look at our red marker, it has 16.9 grams worth of mass, and our water bottle has 1,690.2 grams worth of mass. The red Sharpie marker has three significant figures, whereas the water bottle, because it's further into the range of measurement for our scales in the classroom, it has five significant figures. So we get a little bit more information out of our scale, this specific scale, because our water bottle is further into the range of that scale than the amount of information we get for our red Sharpie marker, because it's not as far into the range of measurement for the scales we're using. All right, so let's work an example here. So we've got two different measurements, all right, 10.7 newtons, which is a measurement of force. So how much two things are pushing on one another. We're obviously going to explore force as we move forward in our study of physics, times 8.2 meters, which is a measurement of distance or of length. So we got 10.7 newtons times 8.2 meters. And you'll notice, so we multiply these two together, we're not limited in the way that we are with addition and subtraction, where with addition and subtraction, we always had to be dealing with the exact same units of the exact same physical quantity. And that followed the same rules as math, right? Where you had to add or subtract like terms. However, when we multiply in math, you could do something like 10x times 7y, right? And when you multiply those together, you get 7 times 10 is 70, and then times x times y. Everything multiplies together, right? We can't add 10x plus 7y. That doesn't make any sense. But we can multiply them together. The same thing with measurements in physical quantities. So we got 10.7 newtons and 8.2 meters. We can multiply those two together. Now, so we'll take the numbers and we'll multiply them. 10.7 times 8.2. If you put that in the calculator, you get 87.74. And then, just like with math, we multiply 10x times 7y, we get 70xy. We get whatever number we get times newtons times meters. So we get 87.74 Newton meters is how we would say this. And of course, we will explore moving forward as we talk more about physics how units interact together. All right. So don't worry about that for now. So, but what you will notice is that the answer we get, 87.74, has a couple of funky things going on relative to the measurements that we started with, right? So first of all, both of them only had a number, or were only precise down to the level of the tenths of whatever their unit was, right? So 10.7 newtons was precise to the tenth of a newton, and 8.2 meters was precise to the tenths of a meter, right? However, the answer we get, the number we get at the end, looks like this goes all the way down to the hundredths. So where do those hundredths come from, right? And if we look at 10.7 newtons, we had three significant figures, whereas 8.2 meters had two significant figures. But the number we get, and this shouldn't be super surprising, it's very similar to when we were adding and subtracting. We end up with more significant figures than we started with, right? So we have four significant figures there. So obviously, we need to reduce the precision, reduce the number of sig figs in our answer here, because it doesn't match up with either of our beginning numbers or our beginning measurements before we did our multiplication. So for multiplying and dividing, what we're going to do is we're going to take, and rather than looking at place value doesn't matter, as we just said in the last slide, and as I'll explain one more time going forward in a second. But what we're going to look at instead is the quantity, the number of significant figures. So 10.7 has three significant figures, but 8.2 only has two significant figures. So just like with addition and subtraction, we'll take the original of the measurements that is the least precise out of the two. So 8.2 meters only has two sig figs, so we will reduce the precision of our answer to two significant figures. So 87.74 Newton meters, we'll round that to two significant figures. So we'll keep the hundreds place, we'll keep the we'll keep the tens place, we'll keep the ones place, and then those are the two significant figures we'll have, right? So we'll round this to the nearest ones place, so 87.74 rounds up to 88 Newton meters. And that should be our final answer here when we attend to our significant figures. Again, for multiplying and dividing, we just want to we want to reduce the precision of our answer down to the number of significant figures of the least precise of our original numbers. All right, so let's take one last look at place value and why it doesn't actually matter for multiplying and dividing. So remember that any of our measurements we can put into a different way to express them, right? So we're going to leave the 10.7 newtons as it is. However, the 8.2 meters, let's change that into a different unit of measure, right? So we're going to keep it within the same framework because obviously it measures distance or length, but we can express this in meters as it is right now, 8.2 meters, or we can express it in millimeters or centimeters or micrometers or kilometers, gigameters, whatever we want, all right? So we're going to express this into kilometers, and if we express this in kilometers, it's going to be a smaller number of kilometers. It's going to be 8.0082 kilometers. And now that we've put this into kilometers, we could go and we could do the exact same thing we just did, taking the newtons and multiplying the meters, but now we're multiplying newtons by kilometers, right? So 10.7 newtons times 0.0082 kilometers will give us a new number, and that number will be expressed in newtons times kilometers, Newton kilometers, and it'll give us a number, 10.7 times 0.0082 gets us 0.08774. Now, again, we run into the same issues we had last time. Our lowest place value of precision is lower than any of our any of the two numbers we used to get this number, right? And our number of significant figures is 4 down here, whereas we only had 2 with the kilometers and 3 with the newtons. And so we run into the exact same problems. And this is why place value doesn't matter for multiplying and dividing, because again, we can shift this place value around because we're not dealing with the same units between these two numbers that we're multiplying. So we don't need to have them in the same place value or expressed in the same unit anymore. So what really matters is the number of significant figures, because that will stay the same no matter how we express these numbers in whatever units we're trying to express them in, right? So when we had 8.2 meters, we still had 2 significant figures. And now when we have 0.0082 kilometers, there's still only 2 significant figures for that measurement of distance or length there that we have for our second number, right? So there's still 3 sig figs for 10.7. There's still 2 sig figs for the kilometers. And now, no matter what, we want to our answer round to the number of significant figures of the least precise measurement, which is 2 sig figs for our distance measurement. So we will again round to 2 sig figs, and this will give us 0.088 Newton kilometers, which is the same number that we got the first time. There was 88 Newton meters is the same as 0.088 Newton kilometers if we accounted for kilometers versus meters. So that's why place value is important for addition and subtraction, because we have to be in the same units, but it is not important for multiplication and division, because we are now dealing with units that are not necessarily compatible with one another. And so the place value can shift around. It doesn't have any bearing here anymore. And that's why we attend to the number, the quantity of significant figures, rather than the place value. All right, so now that we know how to multiply and divide significant figures, let's take a look at the problems from our problem set and run through those. Now let's multiply and divide some numbers. And just like with the adding and subtracting, I completely ignored the dividing. So that's my bad. We're just going to be multiplying some numbers. Again, multiplying, dividing, they both operate by the same rules. So whatever we do with multiplying, hopefully you'll be able to apply it to division as well. So we're going to multiply these numbers. So we got 9.64 times 110. And if you plug it into the calculator, you get a number that I can't just do out in my head. So let's plug that on into the calculator. Yeah, okay, so it's going to work. Maybe, let's plug this on over here. Why it's being so. So we're going to take 9.64, multiply that times 110, and we get 1060.4. So that gives us 1060.4. And this is kilograms times meters per second. So this would be kilogram meters per second, because units, just like variables in math, will just multiply together, right? So if you take 10x times 2y, you'd end up with 20xy. The same thing happens with units, right? So if we take 9.64 kilograms times 110 meters per second, we end up with 1060.4. Some numbers multiply together, and then the units also multiply. So we end up with kilograms meters per second, kilograms times meters per second. So great. And then, but if we go back and we take a look at our numbers here, 9.64 had 3 significant figures, and then 110 only has 2 significant figures. So the number that we get when we put this into the calculator has 5 significant figures, right? So that is more than both of our numbers. And obviously we can't gain precision when we do our multiplication here, right? When we do a mathematical operation with 2 measurements, we are still going to be limited by the precision of the original measurements themselves. And in particular, we are limited by the least precise of the 2 measurements. And so that means we want to limit our answer to 2 significant figures. So we will round this number to 2 significant figures. We obviously, the first significant figure is being the one in the thousands place, and then we will round to the hundreds place. So if we round this, we end up with 1,100 kilogram meters per second. So we took and we rounded to just 2 place values. Again, the highest one is going to be the thousands, and then the next highest is the hundreds. And so we round to our hundreds place value. 1060.4 rounds up to 1100, and we end up with 1100 kilogram meters per second is the number of kilogram meters per second that we get by multiplying 9.64 kilograms times 110 meters per second with the level of precision that we had in those 2 quantities. So now let's take a look at number 2. We got 800 watts times 0.072 seconds. And if we plug this into the calculator, we will end up with some number. So we'll end up with 57.6. And 57.6, and this is watts times seconds, so 57.6 watt seconds, or 56.7 joules, which we'll eventually find when we talk about energy. But don't worry about that right now. We got 57.6 watt seconds. So again, we've got in that number, as the calculator gave it to us, we have 3 significant figures. However, our original numbers, 800 watts, only had 1 sig fig, and 0.072 had 2 sig figs. So just like last problem, we ended up with more significant figures if we followed follow the calculator in our answer than we had in either of our measurements. So we want to limit ourselves to the precision of the least precise of the measurements we were using in our mathematical calculation, which means we want to limit ourselves to only one sig fig. And so we'll have to take our highest place value and round to that, to the tens place. And so 57.6 will round up to 60. So this would round up to 60 watt seconds. And so if we multiplied 800 watts times 0.072 seconds, and we were attending to significant figures, our rounded answer would be 60 watt seconds. Okay, number 3, let's take 87.3 newtons and multiply that times 104 meters. And you'll notice that both of these have 3 significant figures. So in the end, our answer should end up with 3 significant figures as well. And so if we do this calculation, we will end up with some number, 87.3 times 104. That gives us 9,079.2. So 9,079.2. And again, this is newtons times meters. So we end up with Newton meters as our units here, or kilograms meters per second. But don't worry about that. We will eventually learn what's going on with units as they pop up throughout our course. So we've got 9,079.2 Newton meters. However, that number the calculator gave us has 5 significant figures. So we need to round to our least precise measurement, and both of our measurements had the same level of precision in terms of significant figures. So we want to round to 3 significant figures, which means we want to round to, we've got a thousands place, the hundreds, and then our lowest place value with some precision should be the tens place. So we'll round to the tens place when we round 9,079.2 to the tens place, we get 9,080 Newton meters. That should be our answer here. Okay, and lastly, this final question looks a little bit different than the others. It's a little bit wordier, okay? And the reason for that is that I want to explain something here that we didn't really talk about in the slideshow, and it's what happens when we've counted a number or when we have a counting number. So we know that each of our pencils weighs 2.86 grams, and to get that 2.86 grams, right, we would have had to have measured that. So this is a measurement right here. However, the 17, the quantity of pencils we have, that is what we call a counting number. And why that differentiates itself from the measurements we've been discussing is that if we know we have 17 pencils, we're not confused between having 17.1 and 17 pencils or having 17.001 and 17 pencils, right? We know exactly to a level of precision, an infinite level of precision, that we have 17 pencils. So we can treat this 17 just like a mathematician, or just like you would in math treat a number, which means we can throw a decimal and as many zeros after that as we want, and we are precise to that level, to whatever level we want to go to, right? Because again, we counted the pencils, there's 17 of them. We're not confused between there being a little bit of an extra pencil or missing a little bit of that 17th pencil. There's just 17 in total. So that means that we can take this number right here, the 17, even though it looks like it only has 2 significant figures, right? And if we use our rules of significant figures, there's only 2 significant figures here. That's actually a misleading, because since it's a counting number, we don't care about our number of significant figures here because we know it to an infinite level of precision. So it's not going to hamper our precision for our answer. What does hamper it is any measurements we have in our calculation here. And our measurement of 2.86 grams, that has 3 significant figures. And since it's a measurement, we are limited by that level of precision there. Again, the 17, we're not limited by precision because we've counted them. So we know there's 17 exactly. But the 2.86 grams, we're limited by whatever scale we use to measure it. So we don't know the difference between 2.860 or 2.861 or 2.859 grams, okay? So we're limited by precision there, but we're not with the 17. And so when we do this calculation, we're going to plug this into the calculator just like we've done with the other ones. So we'll take 2.86, we'll multiply times 17, and we'll get some number. We'll get 48.62. 48.62. And again, since we had 17 pencils and we multiplied times grams, in the end, the whole total of pencils, the group of 17 pencils is going to weigh something, and that weight is going to be in grams, right? And that's why, again, we didn't even really have a unit here on the 17 because that's just the number of pencils. We didn't have to say pencils because we have 17 of them and they each weigh 2.86 grams. So in the end, our total weight of all the pencils is also going to be measured in grams. And as we got from the calculator, it's 48.62 grams. However, we're limited in precision from any of the measurements that we use to make that calculation. And the one measurement we had was at 2.86 grams, which we had 3 significant figures for. So since we have 4 significant figures in our calculated answer here, we want to limit it to 3 sig figs. So we've got the tens place, the ones place, and then the tenths place will be our third one. So we want to round down to that tenths place. And so we'll end up with 48.6 grams would be the total mass of all of those pencils if we weighed all of them. And again, there's 17 of them. The quantity doesn't limit our precision because it's a number that we know with infinite precision. However, the measurements, like the 2.86 grams, that will limit our precision when we do a mathematical operation with multiple numbers. Okay, so those are all the problems we had in this problem set. Hopefully, you're on a good track in terms of figuring out what's going on with significant figures and doing mathematical operations with them. I am going to have some additional significant figures practice uploaded on our Google Classroom and on this video. And so if you're looking to do some more practice or do some more reading up on significant figures, you can follow those resources. All right. Let me know if you've got any questions. Thank you for learning.